In this short video, I wanted to introduce a few different network representations without going into details, but just that you know that it exists, and if you see that with data you're interested in, it can be useful, then you can check the details on some papers I reference. So the first one is hypergraphs. So a hypergraph can be considered as a generalization of graphs in which an edge is not limited to two extremities. Okay. For instance, this means that you have an edge that has 3 endpoints, which are 1, 10, and 8. So this is a representation. This is another representation here. So it means that the green areas correspond to an edge between V3, V5, and V6. Okay, and this is very useful because in quite a lot of situations, you have data set in which you observe interaction between groups of nodes, groups of individuals, for instance. So a typical example is when you have, 10 students attending the same class. So you want to say that since we know that these students went to the same class, they are linked. So we want to add links between them. But the problem is that if you want to say that all these students are connected because they attended the same class, then you have to add 45 undirected edges. This is a giant click, it's very dense, and it's not convenient when studying networks. So it will be more efficient to use a hypergraph in this situation and say that the 10 nodes are connected by a single edge representing the situation, the reason why they are connected. You have many other examples, for instance, citations, all the authors of a paper. You maybe want to say that they are connected, but if you add an edge between each of the pairs of authors involved in the paper, again, you get some clicks, and it's not really convenient to work with large clicks. So another example is in Bitcoin, you have multi-input and multi-output transaction, and you can have 1,000 input and 1,000 output. So in this case, clearly you see that it's impossible to represent this as a graph because you will have 500,000 links for a single transaction. Okay. So in this situation, we can model it with a hypergraph. The problem is that you need to redefine many notions on hypergraphs. So what is the degree, what is the clustering coefficient, what is all these measurements needs to be redefined. So what many people are doing is actually instead to represent this as bipartite graphs. So for instance, in my example of social network, you will have one type of node which are students and the other type of node which represent class. And so you will have edges between students and classes. And actually you have much more tools for bipartite networks than for hypergraphs. So when you want to use a hypergraph, often it's more convenient to use a bipartite network representation. So same with Bitcoin. In this case, in Bitcoin, you will have addresses involved in the transaction, which are one kind of nodes, and transaction are another type of nodes. And you can have, for instance, edges from address to transaction to say what are the addresses in input of the transaction, and edges from transaction to addresses to say what are the outputs of the transaction. So it's a directed bipartite graph in this case. Okay, another type of network are the multi-layer networks. So they have different names, so multiplex, multi-slice, multi-type, heterogeneous information network. So you can look at this reference, which is also, I think in the end of the slides. for details, for a complete review actually. And yeah, so multi-layer networks are useful when you have several types of nodes and relation between nodes in different layers. Okay, so for instance, in this picture, you have one layer corresponding to street networks, one corresponding maybe to buses, the other to subways, and you can go from one network to the other when there are interconnections. Yeah, so this, you can represent this by multi-layer network, but you can represent many other things. So for instance, here also if you have a temporal aspect, so you have several layers, each corresponding to one snapshot, and you want maybe to connect nodes between layers if they are the same node, or maybe they can interact between layers. So maybe this node is sending a snail mail to this one, and it's so you want to add an edge from this node to this one in the next layer. And so you can have something more generally which is complicated like this. So let's imagine that you have a subway and bus, and you have this for one time and for another time. Okay, so let's see, you can have any kind of any different number of layers, and you can have interaction between nodes in the same layer. You can have interaction between the same node in different layers, or between different nodes in different layers. Okay, so all the situations are possible. Okay, and so, okay, you have your multi-layer network. What to do with it? So again, the problem is how to define what is the degree clustering coefficient, what is commutation on this, and so on and so forth. So there are quite a lot of work, especially in the last few years. It's a very popular topic. But in my opinion, the problem is that there are many ways to do it. And the problem is really that if in the beginning you started to represent it as different layers, is because your layers have specificities. So clearly, you cannot just aggregate everything into a simple layers and say that your degree is just the number of links that you have. In some models, it can be meaningful, and in others, it's not. So, okay, if you, for instance, let's say that you have information coming from different social networks like Facebook, Twitter, and LinkedIn, and so forth, and so on and so forth. If you kept them separated in the beginning, so if you have 10 friends on Facebook, 15 on Twitter, and 5 on LinkedIn, then what is your degree? Well, you can just make the sum. But if you kept them separated, it's probably that you wanted to not to aggregate them. So it's relatively difficult to have a single unique definition of graph measures on multi-layer networks. But there are many propositions in several papers. An interesting, I think, what I will keep as a general idea of this is that if you start with a multi-layer network like this one, you can transform it into a simple graph by doing this kind of transformation in which you identify each node as belonging to by the layer it corresponds to. So for instance, this node corresponds to node 1 in layer A X. Okay, X, you have XY, AB. So this is layer AX, and this is node 1 of layer AX. Okay, so with this representation, you can have this single graph, and you're keeping all the properties. You're keeping edges which are between nodes in the same layer, and you are keeping maybe also edges between nodes which are in different layers. Okay, so this is a representation as a simple graph of a multi-layer network. How to represent this? If you use matrix representation, you can use a supra-adjacency matrix, so something like this, in which, so in this example, you have only 4 nodes, but these 4 nodes below are in different layers. So you have the advice layer and the friendship layer. And you have this advice layer is actually, you have 4 advice layer. You have one which is actually the advice for one node, for the other node, for the other node, and so on and so forth. And so in this matrix, the blue edges correspond to intra-layer edges. Okay, so this is one layer, and the blue or the green that correspond to edges inside one layer. Then you have gray edges which actually link one node to the same node in a different advice layer. And then you have also these darker edges corresponding to interact to linking one node to the same node in a completely different set of layers. So I want to finish with a way of representing networks, which I think is very interesting. And it's also quite an active field of research, which is higher order networks. So it starts from the observation that in many cases we build network based on logs of a sequence of items encountered by actors. So a typical example would be people traveling in public transport. So you can track, for instance, in Lyon, that people are starting from, I don't know, from somewhere in the city center, then they go to Charpennes, then they go to Pardieu, and then they go to ENS de Lyon, for instance. And typically, you will split this in pairs, and you will consider that this corresponds to one trip from one observation of a trip from the city center to Charpennes. Another one is a trip from Charpennes to Pardieu. Another one is from Pardieu to ENS, but you forget that they have been actually done in a specific order. Another example would be people buying products on Amazon. So again, you have the information that this person bought first a computer, and then a mouse, and then I don't know, a keyboard, and so on and so forth. So you have again this sequence of items, but when you're building a network, usually you're just considering the pairs of elements which are just the one after the other. So that's what we are doing in general, but it could be very interesting in many cases to keep this information. So in the paper, when they introduce this concept of higher order network, the authors give this very convincing example of trips made in the US, by plane. That when people come from, for instance, from Seattle, and they go to Chicago, then in most cases their next trip is back to Seattle. Same thing with Atlanta, same thing with San Francisco, and same thing from New York. If you're from New York, you're going to Chicago, then it's very likely that your next trip will be to New York. But if you forget about this history, and you just look at what is the probability when you're at Chicago, what is the probability of the next airport you're going, then you see that the probability to go to Seattle from Chicago is actually only 14%. Okay, so if you forget about the history, you know that you're in Chicago, you think that the next trip has a 14% chance of going to Seattle. But if you remember that you're coming from Seattle, then you can predict that the next trip will be to Seattle with a probability of 83%.
Okay. So how to represent this in terms of networks? So here you have a row, so a sequence of data. And what we are interested in is the relation between M and X, principally, MX and MY. So if you're starting from M, you see that if you're coming from A, so in this case, we are coming from A to and we are going to M, and in this case, we are coming from B, and we are passing through M. So if you're coming from A, then in most cases, we will go after M to X. But if you're coming from B, then in most cases, you will go after M to Y. Okay? So here you have, if you're coming from A after M, you have 3 chances out of 4 to go to X. But if you're coming from B and you're on M, then you have 3 out of 4 chances of going to Y. So if you forget about this information and just look at the pairs of trips, you see that if you're on M, you will consider that you have 50% chance of going to X and 50% chance of going to Y. If, on the contrary, you keep the higher order dependencies and you try to remember that you're coming from A or to B, you can create this, so what we call a higher order network, in which some nodes do not correspond anymore to a single node. So for instance, here you had a single node to represent M. And here, since we consider that it's different if we're coming from A or from B, then we will create 2 nodes. There is the node M coming from A and M coming from B. Okay. And now we can represent on the weight of the edges this information of the difference between the two. If I'm on M coming from A, then I have a 75% chance of going to X and only 25 to go to Y. But if I'm on M coming from B, then I have a 75% chance of going to Y and only 25 of going to X next. Okay, so this is the higher order network. You will duplicate some of the nodes to represent that they correspond to different scenario because of their origin. And so, of course, in this example, there is only a memory of 1. I only remember where I come from just before. But you could imagine a higher order with memorizing 2 paths or 3 paths or even more. What is interesting is that this approach is very convenient when you're using methods which are based on random walk. So if you remember, we have defined measure like PageRank or InfoMap, which are based on the idea of random walks through the graph. And so the PageRank is defined as probability to be on a particular node at any time, if you're moving randomly on the graph. Or in the InfoMap, the communities are defined as the one that best compress a random walk on the graph. And you see that these definitions can naturally integrate this memory. You will just consider that your random walk actually has a different probability to move from one node to the other, depending on where it comes from. So in that case, you don't even need to necessarily represent it as a higher order network, but just on the process of the random walk, you can memorize this information. But in other cases, you can just represent it as a higher order network with really having nodes corresponding to a node and an origin. So in this case, you have a node, which is so a node is now a tuple, actually node and history. And then you can apply any normal algorithm, like for instance, a community detection on this new network, this higher order network. And you observe that the communities are composed of node history vertices.
So this means that naturally now, a node, an original node, for instance, a city, can belongs to several communities. So naturally, for instance, you node or representing, I don't know, Atlanta. If it's Atlanta coming from New York, it can be in one community. And if it's Atlanta coming from, I don't know, Paris, it will be in a different community. Okay, so maybe one community can correspond to business trip and the other one to leisure holiday trip. But one city can naturally belong to several communities because a same city can be represented by several nodes depending on the origin. So I think this is a very interesting representation. The weakness is its complexity in terms of complexity, time complexity, space complexity of the algorithm, because the number of nodes is actually multiplied in this higher order network by the number of possible arrival sources. Okay, so if you imagine on the airport network, you can arrive in each airport from, let's say, in average 20 different airports. So this will multiply the number of edges by 20. And the number of edges will be even more multiplied since you have to still remember from each of the origin all the possible destinations, which are now also multiplied by the number of origin, and so on and so forth. So, so of course, an interesting research topic is to find a network in which you will, a higher order network in which you will keep only those different origins when it's really meaningful. So maybe going to Atlanta, maybe if you come from New York or from Washington, it will be relatively similar and it's not worth representing it as two different nodes. But if you're coming from New York or from Paris, maybe they are really different cases, and it's meaningful to represent it as two different nodes.